Hello, my name is Eric Prud'hommeaux. I will introduce HL7 FHIR representations in RDF as described by shape expressions or ShEx. This is some work being done at Mayo Clinic with Harold Solberg and Guoqin Zhang. I will introduce the web-based graph language RDF, its a schema language, ShEx, HL7 FHIR and its representations in RDF, and why and how to develop and use FHIR RDF. I'll give status updates on FHIR RDF and ShEx. RDF is a graph language based on web architecture consisting of simple statements of a subject and object node connected by a relationship. And ShEx is a schema language for RDF. In the upper left schema, we see that a medication request has a dosage instruction which has a timing which has either a frequency or a when. The when must be in the value set of AC, ACM, ACD, or ACV. The green dosage instruction at the top identifies an RDF property, and the blue at dosage instruction identifies the value type. FHIR happens to use properties and resource types with similar names. The data in the lower right shows that a medication request 123 has a dosage instruction 456, which in turn has a timing 789, and that has a when of ACD, which is in the specified value set. Of course, much of the value of a schema language is in telling you when you're wrong, as it does here because the value AD is not in the prescribed value set. Now on to FHIR. FHIR is a resource-oriented, quickly evolving clinical information model. Resource-oriented means that the reusable components of clinical documents are independently addressable web pages. The standardized structure of these web pages are described in a FHIR-specific schema language. Here we see that a medication order has 0 or more dosage instructions, each of which may have a timing. That timing is its own independent timing resource, described in blue at the bottom. These schema are quickly evolving. For instance, the DSTU2 medication order has a built-in dosage instruction, which has been broken out into its own resource in STU3. So where do these definitions come from? Interop comes from a core set of resources managed by HL7. The development of RDF schemas, examples, and translation tools is cast in terms of these resources. This moving target means we don't want to look at each resource in structure definition and decide what it should look like in ShEx. Instead, we have a general algorithm for translating FHIR structure definitions, which applies to HL7 resources as well as resources developed externally, like DAF or Argonaut. FHIR RDF and its accompanying shape expressions were added to the publication process between DSTU2 and STU3. STU stands for Standard for Trial Use. As we've seen before, these resources have an intuitive HTML representation, which I show here to give you some idea of the expressivity of FHIR schemas. These schema convey a structure with ordered attributes and data types which are enforced in FHIR XML by W3C XML schema. There are additional co-occurrence constraints, such as that the requester's on behalf of field is only allowed if the agent is a doctor. These are expressed in schematron. Intra-resource consistency, such as that the subject is actually a patient, is enforced by special code in the FHIR reference libraries. Fortunately, ShEx captures all of these constraints in the same schema language. As an added readability benefit, ShEx schemas look rather like the HTML if you take out the arrows and icons. So why RDF? Clinical data is really a graph with lots of interconnections. RDF linked data uses web architecture to make it easy to connect your data to lots of existing and emerging scientific or environmental data. Rich terminologies like SNOMED can be defined in OWL, which is expressed in RDF. That means that commodity RDF tools integrate the information and terminology models, so you could, for instance, trivially ask for patients on immunosuppressants after any sort of transplant operation. So how would this fit into your pipeline? During model development, processes can test example data against schemas for iterative refinement of a shared model. Later, production tool chains can involve translations to and from other representations of FHIR or terminologies. I've mentioned the value of expressing both your information model and your terminology model in RDF. This enables queries over clinical records, leveraging the subsumption available in rich terminologies. On the research side, I might want to test which post-transplant immunosuppressants had the best outcomes for hepatitis C. To act on this knowledge in patient care, I could implement special CDS rules for patients at elevated risk for hep C. So what have we gotten out of ShEx? We really needed an expressive schema language to define the FHIR RDF standard. It caught a lot of mistakes, over 400 in fact. As a testament to its maturity, we swapped between a node-based JavaScript implementation and a Scala implementation and found no disagreement between the two, which is to say, nobody noticed. ShEx version 2.0 was released in March of 2017. The W3C community group is continuing with API and language extensions. Some of us are also using ShEx to write rules. An RDF schema is like a regular expression or grammar for a set of RDF graphs. Attaching variable names to leaves in the graph allows us to use the schema as a parser. In validating the data, we create a tree of variable bindings. Attaching those same variable names to leaves in another schema allows us to run the validation process backwards to generate valid instances with leaf values supplied by the document parsed earlier. This is called ShEx map, and it basically translates from one schema to another. These are just a couple of the ways we're using ShEx to translate, validate, describe, and consume clinical data. Thank you for your attention.